Thank you very much, Professor Kellens, for the nice introduction. And thanks to everyone for attending. Today, I will indeed publicly defend my PhD on miniaturized high-frequency matrix transformers for electric vehicle onboard chargers. So I hope at the end of the presentation you know what this means. And I want to really thank everyone and welcome everyone. There's a quite broad attendance today. About 150 people registered, either here and also a lot of people online. So I'm very proud to present my work. I hope this broad attendance means that there's a lot of interest in high-frequency magnetics, or perhaps it's just friends and family or colleagues wondering what I've been doing for the past couple of years. So either way, I will defend my PhD, and for that I will start with a motivation, because to work on one topic for 5 years takes a good motivation, and so I'll share a part of mine. And I'll bring you to an introduction to transformers, what these are and why we use them. And then I'll give you my two main research contributions that I made during my PhD. Now, to start with the motivation, I will start with this, energy. Because energy, the first law that we talk about today, is that energy cannot be created nor destroyed. It can only be converted from one form to another. And so the energy in the scan can be converted by our bodies into movements or into thinking. Or if you give me enough of those, it can be converted into a manuscript. And so when we talk about generating and using energy, we're really just talking about converting energy from one form to another. For instance, from nuclear energy, which we can convert into heat, which then can spin a turbine that a generator can turn into electricity, that can make it over to your house where you can use it to turn on the lights or to cook dinner. Now, also historically, we can see that large steps in our technological advancements have been made possible by new ways to convert energy. For instance, from agricultural era, we've had a steam engine and electricity bring us to the industrial era. The invention of a transistor has brought us to the information era, we can call it, we are in today, with artificial intelligence and TikTok. Now, each of those steps has been initiated by new ways of converting energy and also new amounts of energy that we are consuming as a society. And so I think this will also be the case if we look into the future, perhaps we can dream about the space era. Now, this story of the past and the future also applies to the world as it is today. If we look around on the world, we can see that the development of a country or a society largely depends and correlates with the amount of energy that it consumes per person. And so, improving the capability of accessing energy and converting energy can help societies develop. And there's really nice initiatives that focus on this. Now, all of this is just to say that energy conversion as a topic is not just something to keep engineers busy, but it's a topic with real societal impacts, on human development, on our progress, on technological level, and also on our long-term progress. Now, my work situates in this red arrow, in the realm of electric energy. And there we use what's called power converters. Because there's many ways that we can generate electricity. We can have solar panels, wind turbines, or traditional generation. And there's also many ways that we consume electric energy. You can think about batteries from your phone to an electric car. There's processors in data centers in computers, industrial motors that are spinning, and at your home there's also countless applications. Now, this generation and use has to be interconnected, and for that we use a high voltage grid. So it's kind of a long-distance interconnection. We do it at high voltage. It's very efficient to transport that electricity. But of course, that means that all of this needs to be interconnected. So for that, we use power converters. Power converters are electronic circuits that we use to control and convert electric energy. And so you can see that they're basically everywhere. Sometimes it's visible, like your chargers, and oftentimes it's invisible. It's somewhere hidden in an application. Now, indeed, they are everywhere. Not only that, they also convert large amounts of energy. Just taking one example, we can look at data centers. Their electricity use is already really high. These are basically the computers that run the internet. And so by 2030, due to the growth of AI, their electricity use is projected to double. It's really an unseen amount of growth. It's basically adding 70 nuclear reactors, the size of Doel 4, just for these new data centers alone. Another application is electric cars. We all know electric cars are now quite common on the road, and so indeed their sales are rising quickly. And for an engineer like me, an electric car is basically a large battery on wheels. And so we're discharging that battery to drive the motor, so the wheels spin, but we also have to charge the battery. And for that, you can use the large chargers next to the highway. Oftentimes, though, you use an onboard charger. You have a charger built inside the car that you use when you charge at home or at work on these small kind of interconnections that you use. Now, that onboard charger indeed is built into the car. It's kind of like having an iPhone charger built into your iPhone. If that were the case, you want it to be small. Now, the problem is that this charger in the car, it's about 1,000 times more powerful than a phone charger, and so it's also larger. It's about the size often as a crate of beer. And so we're carrying this around everywhere we go, and that means that it's consuming energy for carrying it around, and it's using space that we would rather use for batteries, for luggage, or for passengers. Now, if we open up that charger to take a look inside, it's kind of like a puzzle of thousands of components, but one of them really stands out to me. Here in blue, we can see the transformers, and they often take up about 1/3 of the size of that charger. So we can imagine a future where these are really compact, and perhaps we can go to chargers that are about the size of an iPhone. Then we save a lot of space for other things that we like to do in the car. So that's basically the motivation that brought me to this manuscript, with the title of Miniaturized High-Frequency Matrix Transformers for Electric Vehicle Onboard Chargers. And the central objective is to conceive and demonstrate new magnetic design strategies that can fundamentally increase the performance limits of these devices. And by doing so, make miniaturized transformers that allow us to substantially increase power density of a converter. Now, us researchers, we like to make simple things really complex. Today, I'll try to make my explanation of my thesis as simple as possible. So starting from this sentence, this basically means that I'm trying to make tiny transformers that allow us to make tiny converters. And so I do that in my dissertation. It has six chapters. I start with a thorough description of what's already been done and all the background. And I have two main contributions in chapter 3 and 4. That's the field-balanced windings and snake winding. And with those, I present novelty to this field, and they are all supplemented or complemented by material in the appendix, and there's also secondary contributions of other work I did in a lot of the appendix. But today I'll really focus on these two contributions that I put forward. Now, before I go into that novelty, I want to introduce everyone to what's a transformer, right? Because not everyone is here an electrical engineer, and even within the realm of power electronic engineers, not everyone is really has expertise on transformers. It's kind of a niche topic. So I hope to bring something for everyone. So what's a transformer? Well, perhaps half of the room, there's also kids here. So perhaps you're all thinking about this guy. Now, luckily, I will not talk about this one. To me, what I talk about is just as interesting, but we start very simple with an electric wire. So it's just a wire of copper that we can run a current through. And if we do so, what's interesting is that magnetic fields form around that wire. These magnetic fields are formed by what I call the first law of magnetics today, is that electric current induces or creates magnetic fields. And so we can use that to take a block of iron and now wrap our winding around that block. If we then connect a source to it that pushes current through that wire, we will form the magnetic field inside the iron. It's kind of channeled and amplified inside the block. Now, by doing so, we will have converted electric energy into magnetic energy. And where the real magic happens is if we take another block and we wrap a wire around the block and we connect a lamp. Now, there's nothing powering that lamp, so it's not turning on. But watch what happens if we put the two blocks together. Now the magnetic field created by that first winding, the primary, gets caught by that secondary winding, and there the lamp will start to shine. And here the second law of magnetics is that it's not only electric current that creates a magnetic field, but magnetic fields can also create electric currents. And so we use that in a transformer to take electric energy, turn it into magnetic energy, and then back into electric energy. Now, what's really cool is that these two parts don't even need to touch each other. They can be separated by air, and still the field induced by the primary will be caught by the secondary, and we get a current that turns a lamp on. Now, why would we use this? The first reason is for safety. We can have two circuits completely separated from one another and still power running through. So we can, for instance, have a very high voltage battery connected to something that you are using or touching, and it can be safe for you to touch. And we also use this to create that high voltage in the transmission lines that we talked about earlier. The second reason, however, is for voltage and current conversion. Our electric energy exists as a product of voltage and current. This defines how much energy we can transmit per second. You can think about voltage as kind of like how much energy each charge has, and the current as how many charges we're pushing through per second. And so these two define the electric energy. And so if we take this configuration, we put 400 volts on the primary with 10 amps, we also get 400 volt and 10 amps. Now what happens if we do twice the amount of turns on that secondary winding is that suddenly we have 800 volts. And the same applies if we take less turns, we get 100 volts. So we can very easily change the voltage and current ratio just by the amount of turns we use in our transformer. So now you all know what a transformer is and how it works. Then I talk about miniaturization, so how can we make it small, and what defines the size, because we don't want transformers this large everywhere, right? So they can be this large, but we want them to be as small as possible. And so what determines the size of a transformer is its power, so how much energy per second it's transferring, as well as the frequency it runs at. Frequency, you might know that the electric grid uses 50 hertz. Now, many of our converters use 100 kilohertz. There's even converters running at 1 megahertz. Now, the larger the higher the frequency, the smaller it can be. Now, what is frequency? Well, to excite the transformer to create a magnetic field, we're kind of chopping up the voltage in parts. And each time we chop up the voltage, we create kind of packages of magnetic energy. And at 50 hertz, we create 50 packages of energy that the transformer is converting. At 100 kilohertz, we're doing 100,000 packages per second. Right, so we can increase the frequency. Now we do 200,000 packages per second, and we can go to 500,000. And we can see that as we increase the frequency, also the size of the packages gets smaller. Right, so 500,000 packages get smaller in size. So the magnetic field inside the core is lower. And that means that the core can also be lower, can be smaller, sorry. So we can push this further, and why not run it at 1 megahertz, 1 million times per second, and make a really tiny transformer? Well, the problem here is that not all the energy that goes into this transformer also comes out. So we have some energy loss, and this is manifested as heat. And this heat is causing the temperature to rise, so we can overheat the thing. The problem here is that as we increase the frequency, the energy losses in the wires that we are using are increasing. And so as we use that principle to make tiny transformers, the heat goes up and our device will overheat. And there I have a lot of experience with doing exactly that, with making transformers that get too hot. And so basically my work has been to make really small transformers that don't melt or don't overheat or in any other way cause a failure. So my first contribution leads from this, and it's the field-balanced windings. And here we're exactly trying to reach high frequency in our transformers. And as an analogy, I want to start with an intuitive explanation, and we can look at a river where water is running through that river. The water through that river can be an analogy, can represent the current running through a wire. And so if we run it at, or if we run our transformer at low frequency, like 50 hertz, the current is going through the whole river. And so with that, we have low energy losses. Now, what happens as we increase our frequency to 1 megahertz is that suddenly whirlpools start to form in our river. So there's water just circulating through the river. And that means that on one side of the river, the current is accelerating, and on the other side, it's slowing down. Now, since the water is just circulating and not contributing to the output, this means that the current density gets worse and there's more energy losses associated to this because that whirlpool is dissipating energy. And this is the principle that's kind of the challenge we're trying to solve also in the wires. Now the solution, also in an intuitive way, that I'm proposing or that I'm working on is to have an additional whirlpool that works in the other direction. So say from the top side, a whirlpool gets created that's in clockwise direction. From the bottom, we're trying to also induce a whirlpool in counterclockwise direction. That way, on the two sides of the river, the two are canceling each other. And as an effect, we only have some slowing down in the center, but overall, the current can now use both river banks. And with this, there's a better current distribution through the river, and there's less energy losses associated with it. Now, that's the intuitive kind of explanation. Now, let's have a look at how we can implement this in a transformer. Once again, we use a magnetic core, a material that conducts the magnetic fields. And we have a winding now formed on printed circuit boards where we can make really thin plates of copper, but still create those loops around the wire, around the core. And there's two areas that are important for the power, is the area where the magnetic flux goes through, the core area, and the area where the current goes through, the winding area. And so these two define the power, right? Now if we take a section of that core and we zoom in to the winding area, we can see that again we have these primary loops and secondary loops, and now we just put them above each other. They're still isolated from one another, but it's just a different geometry as before. And so still those primary loops are inducing a magnetic field, and the magnetic field gets caught by the secondaries, so to say, and gets reduced, creating that output current and voltage. Now, the problem here is that the magnetic field doesn't only exist in the core, but it also exists in the spacing between those different loops. And so we can see in simulation results in red color that the magnetic fields in the center of this structure get really large in that isolation space between the layers. And with that large field at high frequency, we get those whirlpools that get induced. And we see also that reflected in the current distribution, where indeed we see these large spikes, and there's even negative currents running on the other side of that conductor. And so these are dissipating vast amounts of energy in a way that indeed, we cannot run it at these high frequencies without melting it. The solution that we typically use to this is to interleave those primary and secondary loops. So we can have a primary loop and then immediately below it a secondary loop, and it's kind of catching immediately that magnetic field so it doesn't build up throughout that structure. So we reduce the height or the amplitude, let's say, of the magnetic field, and in that way we improve the current distribution. But still you can recognize in the current distribution that kind of all the current is crowding to one side. We still have those eddy currents, those whirlpools in our conductors. If we zoom in to two of those conductors, we can see it's because of how the magnetic field is kind of like situated around the conductor. The boundary conditions of this is that on one side it has a field, on the other side it doesn't. And this is creating eddy currents in a way that this is in phase or in the same direction as the current on one side and out of phase or in the opposite direction on the other side. So we get what we already saw before. Now, we can imagine, as before, also what we want, and that's for currents to run on both surfaces, right, reducing the energy losses. Now, to realize this, we can imagine the eddy currents, those two whirlpools that exist, and to induce those whirlpools, we can then think of the magnetic fields that would create this kind of system. And the condition for that is for the fields to be balanced around the conductor, so on the top side and the bottom side to be equal in amplitude, but opposite in polarity. And this will create the system that we're looking for. We can make a winding like that and validate it also in simulations, and we can see indeed the fields are reduced, plus the fields are now creating the system where current gets to both surfaces, and even at really high frequencies, we get really good current distribution, nearly the same as if it was being used at a low frequency. So that's the principle that we're trying to achieve and the benefit it can give. And at really high frequencies, this reduces the energy losses in the windings by a factor of 2. So there's a really large benefit we can gain from this. But how to make it? That's where another contribution of mine exists. And for this, I'm building on previous works that have already identified some of the benefits, really, of these kind of structures. It started in DTU around 2009. In MIT, around 2018, they presented a lot of the analysis around it, and they presented an inductor, so a different type of device that achieves field balancing in a single layer design. However, while they present a lot of benefits and potential, this doesn't translate to the transformers that we're trying to build. And at ASU, at Texas University at Austin, they also already did transformers that achieve it, but these still rely on specialized winding structures, such that it's difficult to achieve in any transformer with more considerations. And that's the contribution I make, is to present 3 new methods to realize field-balanced windings in a very practical, easy to implement way. And so I presented in the thesis with kind of flowcharts to choose which one to use in which situation. But overall, these can apply indeed field-balanced windings in any type of transformer, no matter the parameters. Basically, if you can do interleaving, the sandwiching, now you can also do field balancing. And I present just one example of how this can be done to show how simple it can be. And for that, I use an example of a transformer with a 1-to-2 turns ratio. So that means for each primary, we have 2 secondaries, just like the example before where we have 400 to 800 volts. Right, in this case, the secondary current is half of the primary current. And so if we do an interleaved structure, we will do 2 secondaries of half the width of a primary next to each other. And that means that each layer has the same total current. And so in that case, we get an interleaved structure looking like this. Now, how to turn this into a field balance structure? We just duplicate it, and we add an empty layer in the bottom, and then we move that secondary from the top to the bottom. This way, the 2 outside layers have half the current of all the inside layers, and we get the magnetic field distribution that we are after. So it's a very easy, elegant, and unique way to achieve field balance windings without relying on specialized winding structures or parallel currents, as is the case in all the prior art. Now, that's the case, and we understand how it works, then we can see that the benefits of this is that indeed we can run our transformers at high frequencies because of it, or we can use thicker copper because now we're using 2 surfaces of the copper. And we can do a combination of the 2 and then find a system overall that penetrates all the relevant performance indicators of a transformer, from lower losses to lower volume, as well as lower parasitic effects such as parasitic capacitance and leakage inductance. Now, to demonstrate these benefits, I do a full parameterization of a transformer, the one you see here. So that means I take the transformer and we can vary all of the sizes. We can change the geometry, we can change how many loops we're using, etc. And for each one, I set up the mathematical models to calculate what will be the losses in this case, what will be the temperatures, what will be the parasitic effects. So that allows us to run on our computer. I did 1.2 million cases, for example, and find the best ones. So we can see which ones have the lowest loss and which one have the lowest volume. And the ones I show here, kind of each square is one possible design we can make with its associated losses, temperature, and volume. And so we can choose one. And this is the case for interleaf windings, so the previous solution. If I do the same for my field balance windings, we can see that overall, each design gets better. Like the optimal designs can do lower losses, around 40% lower losses, or around 40% smaller, or a combination of the 2. And so here we can see really on a whole holistic level what the benefit can be. Now, to demonstrate it in real life, I present in my dissertation a lot of experimental work. 2 different transformers were built for 2 different converters. And you can find all the results in the thesis, but across them, I demonstrate primarily that we can run it at high power, high frequency, and with a high peak efficiency. And so that means that we're kind of achieving what the field balancing is after, that we can increase the frequency at a certain power level. And so I did so for a 400 to 800 volts DC-DC converter for onboard chargers. And if we compare this to any of the previous kind of converters, transformers, I should say, in other publications, we can see that we achieve the highest frequency operation at this power level, or vice versa, compared to any transformer prototype that we had before. So that was my first contribution. I hope at this point you still don't need one of these to go to the next contribution, because this is a snake winding matrix transformer. We can also it here. So I brought the prototype. You're welcome to have a look afterwards. There's some PCBs there. They're not to take home, but they're just so you can have a physical look at how it looks, and you can also get a sense of the size, right? And we will end with what this thing exactly is. But here we are targeting flat magnetics. And so inherently, it's pretty difficult to make a transformer flat. Well, why is that the case? Because as we saw before, a current creates a magnetic field, but this magnetic field is at a 90 degrees angle. So automatically and inherently, these transformers favor to be kind of a 3D boxy shape. Now, we can flatten those in different ways, and the first strategy is to just kind of squish the transformer, so have the same areas for the current to go through and the magnetic fields to go through, so theoretically they can handle the same power. But by flattening it, now we're also enlarging the loops that the current and the flux need to make. And so there's more energy losses associated to that. The second strategy is to use not just one large path for all the flux to exist in, but to split up that path into several parallel paths. In this case, 2 parallel paths, and so each of those can have a smaller cross-section, and the device can be flatter. And this kind of shape is what we call planar magnetics. And this is very often used in industrial solutions. Perhaps your charger will use one of those. The third solution that's very popular in research and development now are matrix transformers. Here, instead of just having one transformer that we're trying to manipulate the size of, we can also choose to add multiple transformers and interconnect kind of a range of smaller ones to operate as one large transformer. And so that matrix transformer, you can perhaps already have recognized this in the previous chapter, where I already implemented this with the field-balanced winding. Here we have 4 pillars of magnetic material, and each of those pillars is kind of like one transformer that we have primary and secondary loops around. And so the problem here is that routing those turns around those pillars is kind of like playing the game of snake. We have to make sure that we are doing the right direction around all the pillars, but we have to avoid biting our own tail. And so sometimes you get stuck, so you need to duck underneath, kind of like 3D snake, and then complete the path there and go back up. The problem is that connecting different layers comes with interconnections, we call it vias in this technology, that are kind of like dead zones for all the other current loops to exist in. You can kind of recognize here that we have to avoid those areas, and so they're dead zones that are not contributing to the transformer. And so this is very difficult to achieve. I had a lot of issues, and it took me a really long time to build just one. And so you can see that for a 4-pillar transformer, that's already the case. Now imagine if we're trying to do 16 pillars, or even more, 24 pillars, etc. Now the solution is, some of them are here today. I have a lot of older brothers and sisters. And so my first phone was this one. And we can think about the game of snake to solve this issue. How can we go around all those pillars in a pattern that goes in the right direction everywhere, and it also fills up our whole area, avoiding the pillars. And then we can have this kind of solution. And now we can have many turns without any via connections, right? So we're solving this scalability issue. Now going back to a technical drawing, we can do the same for a grid of 16 pillars in a 4x4 formation. And we can see that indeed we're solving termination and routing issues. Now the real interesting thing happens if we take another layer and we mirror that first layer. Then we can use those two underneath each other, and we can see that they become complementary. Because that first layer sometimes only has a half turn around the pillar, sometimes a quarter, sometimes 3/4. And a second layer now automatically creates the complementary part of that loop. So we ensure that each pillar sees exactly one complete loop, and this in turn ensures that the flux induced in each of the pillars is the same. And that's really important in these types of devices. So that's my contribution I also made to this field. And the second part is to recognize kind of a synergy of features that goes to extremely flat transformers. And there, we really shift the paradigm, I said before, of instead of thinking about looping fluxes and current around each other, this becomes kind of like a weaving pattern of fluxes and currents that become a really tightly knit kind of grid. And so we already know 2 features of that synergy, but there's 4 more that complete the circle, and they're kind of enhancing each other in a way. I'll go into a bit more technical depth on 2 of those, and I really invite you to have a look or discuss the other ones. But a really important feature is also kind of the flux distribution through that transformer, so how the magnetic fields look. And so our snake winding is inducing the flux in the pillars in a checkerboard pattern. So some of them are having upward fluxes in purple, some downward fluxes in red. And we kind of interleave, or we can kind of switch those in the pattern in a way that in the center, each of the pillars where the flux goes up, it can go down in 4 neighboring pillars. And that means in the plates where the flux crosses horizontally, we can have very thin plates because there only a fraction of the flux exists. So in the center, only a quarter, and some of the edges, only half of a flux. So the plates themselves, those large parts, they can be extremely thin and still have low flux density, low magnetic fields existing in the plates. So we can make really flat transformers without saturation or excessive losses. And we can even solve the issue of those corner cases having only 2 neighbors by extending the core a little bit there, covering the windings. This also helps with EMI. But this kind of locally enlarges the cross-section, so the flux density there also gets homogenized. So we get, in the end, a very flat transformer with low fluxes and low losses. What's also interesting is that these flat transformers are really easy to cool as well. We end up with a large footprint, really short paths for kind of the heat to dissipate through. And so comparing the snake winding case with a more conventional 4-pillar case, giving them the same heat losses in the core and in the windings, we can see that the snake winding transformer achieves much lower temperatures. So we can really push this to way higher powers. We can increase the current density and flux density and so on. I like to think about this as trying to heat up a pancake. If you're trying to heat up a nice Belgian pancake, they're really flat and large, so they're easy to heat up in the pan. If you take a stack of fluffy American pancakes, then in a pan, they will take a long time to heat up. It's kind of the same as we're trying to cool it from the bottom in this case. Now, overall, these were some of the features that kind of amplify each other in going to a really flat transformer. And we can see it in the examples. It can become the size of about an iPhone or a pen. I just want to highlight one example of how this kind of works, and if we go from small grid to large grid, what it implies. And for that, I show a case for a 6.2 kilowatt onboard charger, where we do 4 pillars, and then we can calculate what will be the size of the transformer we need. And we can enlarge the grid to 3 by 3, and we can see that by increasing number of turns, also the pillars can get smaller. So as we add pillars, each of those gets smaller, so it's kind of favorable scaling, we can say. And besides that, each time we add pillars, we can also reduce the height. So once again, as we go for 4 by 4 or 5 by 5, we can still make it, and we can keep downsizing the total height. Now, if you just want the optimal volume, the 3 by 3 in this case will be the best. But what's interesting here is that by increasing the grid size, we can keep going lower in height. And this can be interesting in certain applications. And what really stands out is that even in this quite conservative first-order analysis, we can see that there are designs that exist that are 1 kilowatts of power per millimeter of height and above. And that's interesting because no transformers exist yet that achieve this. So I look forward to hopefully making one that does so. Now this kind of works for one charger, and we can play with a lot there, but it also works for all kinds of applications. So in my thesis also present how we can generalize this to any turns ratio. We can use series parallel connections, so it's very flexible for all kinds of applications, all kinds of requirements for the transformer. And so one example, let's take 10 by 10 grid. Let's wrap 2 windings around each pillar. We can still do so with only 2 layers of copper and only 2 interconnections. So that's all theoretical background and analysis and validations. Of course, we have to demonstrate also if it works in real life. So we have to build a transformer and we have to test it. And so this is the not so pretty side of how it looks in the lab, right? But that's the reality. And here it's kind of set up so we can run these converters that we built with it at high power, the same powers that you can achieve in an onboard charger, and the same voltage levels and everything. So we can really put it to the test. And the prototype we built, I built together with colleagues of mine, is shown here. This is the one I also show today. And so in this prototype, we have a snake winding matrix transformer of 8.6 millimeters high, transmitting 6.2 kilowatts of power. So it's a very high power device with a very low height. And as you can see, the rest of the converter is very flat on itself. And there's also a small plate here, just a 3D print. So overall, it's an extremely flat device. And the main thing is that here we can also make the transformer this flat. This got to the point where we even had to redesign the whole converter just because the gate drivers of the switches and the output capacitors otherwise would stick out. So there's a lot of engineering behind it. But we can operate this with this transformer, as you can also see. And we can achieve here full operation, also 800 kilohertz, 400 to 400 volts. And we can do so with clean waveforms. So we also have low parasitic capacitance. And of course, what's important for miniaturization is the temperatures. And here we can see that indeed we can keep the temperatures low. So we can run at steady state power while temperatures are not rising anymore, up to 6.2 kilowatts. That's what we tested so far. And so basically, what this means is that we can do 6.2 kilowatts in this volume, and that means it has a volumetric power density of 40 kilowatts per liter. Now, what does that mean? We can contextualize this against other works, and we can see here a plot of each dot representing one prototype shown in literature with their power density and their peak efficiency. And so we can see that gradually throughout the years, there's been incremental improvements to increase the power density. Now, my first chapter's prototype also sits kind of in this range with competitive numbers, but there's still a lot of room for improvement, we have to admit. Now, recently, this is really put in perspective by works at Virginia Tech University in the US, where they made a prototype of 30.5 kilowatts per liter. And they do so in an impressive three-phase CLLC converter, having 16.5 kilowatts of power, also in a quite compact 20.5 millimeters. And for that, they also present a very state-of-the-art transformer. Now, our device has achieved that 40 kilowatts per liter, so we're making yet another substantial leap beyond the state-of-the-art. Right? And we can show that with really flat transformers, we can achieve extremely high power densities. And in the end, we can come to transformers that are about the size of a phone, right? So the thickness is already there. We can still work on the footprint to also meet that. But overall, okay, this the achievement that we present with this novelty. And there's a patent pending for this technology. And I do have to say that these are the contributions that I presented today, but these don't exist or they weren't developed on an island alone. These really exist in a larger picture of research internationally. The matrix transformer itself was already presented by Dr. Herbert in the US in 1984. Professor Ngo at Florida University presented a lot of mathematical background. And in recent works at Virginia Tech University, CPAS, by Bin Lee, Ahmed Nabi, and Jin, even from the start of my PhD, really kind of inspired my work in this field. So there's a lot of work in the international community that directly or indirectly inspired these findings. Okay, so with that, we can conclude. And in conclusion, I hope to have shown that from that first converter we saw, we can come to really small prototypes. And so the fact that new magnetic design strategies can be used to fundamentally improve the performance limits of a transformer. And so that way we can create miniaturized transformers that in turn allow us to make substantial gains in the power density of our converter as a whole. And so I kind of show today only half of a picture, half of the circle going from what's in industry now into what we can do in the lab. The next step is to valorize this, so to try to put these technology and transfer it back to industry. And that's what we will do our best to do. So hopefully one day you can have a really flat transformer in your car. And besides the cars, I demonstrated for EV chargers, but that isn't the only application where it can be relevant. I also look forward to applying this to, for instance, AI chips or aerospace solutions, where not only the power density is interesting, but we can really do new things that otherwise cannot be done. And with that, I present some of the publications I made. So I published 4 journal papers. I kind of make up this thesis as well as one submitted. and contributed to others. There's 2 patent applications that came from this research, and I was honored by 3 awards. And there's a lot of conferences I got to present my work at and contribute to with colleagues that are here. But overall, these are just the numbers. Of course, the journey, the PhD is mostly a journey. For me, it was a journey of magnetics research. I did all kinds of different areas of research. I started on controllable magnetics. Then in the second year, really went deep into the trade-offs in planar magnetics. I worked on integrated magnetics, kind of taking different magnetic components and trying to combine them. And as you can see, none of those got it to the presentation today because of the 2 last developments I made, the field balancing and the snake winding, which I really see as 2 contributions that can have an impact really on these designs. So that led to the defense of today. And there's other prototypes kind of combining different works already in testing or in prototyping. But overall, the PhD is just the start of a journey. So I really look forward to what comes next. And with that, I want to once again sincerely thank everyone for attending, and I'm really happy to address any questions.